So it's time. Bamshad, maybe you would like to start.
Sure. All right, let me share my screen here.
Okay, no problem. Let me stop sharing mine. Mm-hmm.
All right, can we see?
Yep.
Okay. Well, welcome everyone to workshop on context-aware recommender systems. This is our third workshop in the second incarnation of the CARS workshops. We did actually have a series of CARS workshops earlier in the history of RecSys, and then we had a hiatus for a few years. And then as we saw increasing interest again in the context-aware recommendation domain, we kind of recreated or created a new version of the workshop focusing on some of the new challenges, including latent context, for example, and some of the other more novel domains and types of contextual information. So this is what this workshop focuses on. And we have an interesting program for you, and hope that you can all participate in some of the discussion and questions and answers. So you see all of the organizers of the workshops on this slide: Geras, Konstantin, myself, Francesco, Alex, and Moshe. And we are all happy to be with you today. So as part of the program, we have 3 keynote speakers, all of whom are going to address the various issues related to context-aware recommendations from different perspectives. So we have Alex Kartazoglu, who is going to talk about the context-aware recommendation from a machine learning perspective. We have Li Chen, who's going to talk about user feedback and recommendation in conversational systems. It's kind of a user perspective on context. And we're going to have Yong Zhen, who's going to be talking about extending context to multi-entity or multi-stakeholder kinds of recommender systems. So all of these should prove to be interesting talks, and we'll have plenty of opportunity for discussion. We also have some contributed papers dealing with various aspects and various domains where contextual information is very relevant, including a paper on context in music recommendation, a paper on predicting budgets and purchase intents, dealing with quality of service, so we're using that as context, and also in the context of session-based k-nearest neighbor recommendation. So for each one of these papers, we'll have a short presentation from the authors, and we will have approximately 5 minutes for Q&A at the end of each one. So just some, if you're going to engage with the discussion, you can turn on your camera, and during the talks, make sure that your mic is muted. And actually, Moshe, is there access to the chat on Zoom, or should the questions be posted on Huwa?
Most of the questions will be on the Huwa. We don't have any chat here in the Zoom.
Right, that's what I thought. So you can ignore that point about posting on Zoom chat, but there is a Huwa page for the workshop. You can go on there, and I think each one of the papers is going to have their own basically detailed page. So when you go to the detailed page, you can post the question, similar to what I guess we've been doing on the conference. But then we'll come back to the Zoom for the discussion and for speakers to answer those questions. Okay, so all of the material for the workshop, presentations, papers, the programs, everything is online on the website. That's carsworkshop.com. I think that is sort of a quick synopsis of what's going to happen. Hope that you can all enjoy it. And I'm turning it over to Konstantin, I believe.
Yep. Yeah. Thank you, Bamshad. So Alex, can you please start sharing your screen while I'm introducing you? Alexandros. So it's my pleasure to introduce Dr. Alexandros Karatsoglu, who is currently working as a research scientist at Google in London. Alexandros did his PhD in kernel methods and open source software. He started working on recommender systems right after his PhD, introducing ranking techniques for collaborative filtering, tensor-based, context-aware collaborative filtering, and session-based recommendations. Alexandros currently works on reinforcement learning for recommendation systems and interactive recommendations. Today, Alexandros will talk about machine learning perspective to context-aware recommendation methods. Alexandros, are you still with us? Alexandros. Okay. Let's wait for a second. He was here and just disappeared.
In the meantime, we can also say hello, everyone. My name is Moshe. Kostya, if I for each presentation, for each keynote presentation, we will have 35 minutes. So basically 30 minutes for the presentations and 5 minutes for questions. And as for the papers, we have 15 minutes, 10 minutes for the presentation and 5 minutes to Q&As.
Okay. Alexandros, I will track your time. You have 30 minutes, as Moshe said. So it would be great if you could see me during your presentation. I will show you warnings, 5 minutes, 3 minutes, 1 minute. Okay, you have 30 minutes and 5 minutes for questions. Please, Alexandros.
Can you see my slides, by the way?
Yes.
Okay, that's great. Okay, cool. Thank you very much for the introduction, and thank you also for inviting me, and thank you to all the participants to join to the workshop. I think it's great that, you know, even during these times, RecSys is such a vibrant community, and we have these nice workshops, and it's pretty cool. Yeah. So yeah, I'm going to talk about a little bit of the work we are doing really at Google, and also with my collaborators that are not at Google at the moment, like Chin, Paula, John. And I'm going to talk basically about two projects, which have to do with context, and I would say two different types of context. And let me explain what I mean. Okay, yeah. So we all sort of know the traditional type of context, and you know, when you let's say try to do a recommendation on and you take into account the location of the user, if he's at home, at work, etc., or the date, or what time it is, or if it's a weekend or a weekday, or potential weather, right? When somebody's potentially asking for a restaurant recommendation, if it's an outdoor location or indoor location, right? So these are sort of the traditional types of context that we know, and we can potentially characterize them as external context, right? It's something that is a user, it defines his environment, and it's not something that the user is telling us about. It's probably something that we already know by whatever kind of information we have during the recommendation process, let's say, right? So this is, let's say, the sort of traditional type of content that there's many methods, and I'm going to talk a little bit about one of the works that we've done with some new techniques in that area, right? And the second type of context I wanted to sort of talk about a little bit is essentially the context that the user is telling us maybe implicitly himself, right? So think of a user trying to shop something on an online e-commerce store, right? And he started to click on laptops and computer hardware. So in that respect, we already should understand or should know that the context of that user session is the purchase of some electronic equipment, and that recommending in that session may be a some shoes or something like that, even if they are relevant to the user in the long term, might not be sort of appropriate, right? So in that respect, the user defines the context himself, right? So this is in some sense the defined context of the recommendation. No? So I'm going to talk broadly about these two types of context and what kind of method we are working on in that area, right? So the first one is really based on graph convolutional networks. And graph convolutional networks are increasingly popular machine learning techniques, deep learning techniques, although they don't necessarily need to be deep, but typically they are stacked, right? So you find them in many layers. And the way you want to think of graph convolutional networks, or the way they actually work is very simple, right? Without going into any of the mathematical notation, the main thing that graph convolutional networks do is they take the representation of a given node and add to it the representations of the neighboring nodes, right? This makes the representation of that given node similar to the nodes of his neighborhood, which is something intuitive, right? We can assume that nodes that are closely connected to each other should be similar, right? In the same way that on social networks, you are a little bit similar to your friends, and vice versa, right? So that sort of property is encoded in the graph convolutional network. So we essentially start with a random node representation for each of the nodes. And by doing this kind of computation node by node, right, taking the node representation and adding to it an average of the neighboring nodes, we get a robust, let's say, representations of each node in the graph, right? And obviously this operation can be stacked, right? It can be done multiple times, and the resulting node representations can be then used on downstream tasks. For example, for the typical sort of example is node classification, right? You have bioinformatic applications, et cetera, even classifying words, et cetera. So there's a lot of work has been done on that. So this is the main idea behind, let's say, graph convolutional networks. And if we look at the recommendation system problem, or let's say the classical recommender system problem, where you have, let's say, the typical users and items, you have some kind of rating matrix where you have, users rating items, and this is very sparse, obviously, and you can represent that as a graph, right? You can represent exactly the same data as a graph, where you have two types of nodes. You have users and items, and they are connected with each other. And in the case of ratings, they are connected with different types of edges, but we can even forget about that. We can assume implicit data, and then basically you just have connections or you don't have connections, right? You have connections when the user interacts with an item, and you don't have connections when the user doesn't interact with an item, no? And so you have this bipartite graph that is formed by this data. And now, obviously, one thing you can do is take this bipartite graph, run graph convolutional embeddings, graph convolutional networks on this, use this graph for graph convolutional networks, and then generate representations for the users and the items using the graph convolutional networks, and use these representations to do essentially recommendations, right? You can compute then the similarity between the user and the item just using these representations that you have computed. And this is actually work that has been already done. One of the papers that has been published, and actually that this figure is from that, is graph convolutional matrix completion by Berg et al. But there's other work that has been done in that area as well. And that's nothing new. So we basically took this concept, let's say, and tried to sort of extend it with a sort of traditional notion of context that I just mentioned at the beginning. No? And this traditional notion of context, you can think of it in this way, right? You have some kind of, let's say you have a user, right, Johannes, and you have some kind of item that Johannes is interacting with. In this case, he's listening to a song, right? And now you have all of these context dimensions, right? You know that he's in Copenhagen, it's a Saturday evening, and the previous song that he listened to was a song by Coldplay, right? So you have this kind of context, and now can we actually find the representation for this context so that we can apply this context on all this information, let's say, so that we can apply graph convolutional networks on it, right? And in some sense, it's actually relatively easy. You can think you can think, and this has been done in the past, you can think of as, you can think about context-aware user item interaction. You can represent an array, I should say, where you have the users at the rows, the items at the columns, and then the context dimensions are the additional dimensions of this tensor or n-dimensional array, right? In this case here, we have only one additional context, so we have a 3-dimensional array. And now this 3-dimensional array is obviously going to be quite sparse as well, right? Because you have users interacting with items and in a particular context, and not all users interact with all items, as we know, right? So this is a sparse sort of, has very few entries, if you like. And we can represent that, potentially move that a little bit. We can represent that array as an n-partite graph, right? In the previous case, we had a b-partite graph where we had only 2 types of nodes, users and items. And here we can have n types of nodes, right? We can have users, we can have the first context dimension, the second context dimension, and in the end, we can have items. And now the context dimensions will connect with the users whenever interaction in that particular context with an item happens, right? So you have a user interacting in a particular context with an item. So you connect the user with that context and the context with that item and the item with that user, right? So you have this kind of 3-way, in this case, connections, but obviously you can have n-way connections if you have more than one context dimension, right? So again, we have formed this graph, right? We have formed this n-partite graph, if you like, right? Not a b-partite graph, but an n-partite graph. Now, the intuitive thing to do here is again to apply graph convolutional networks, right? And that's exactly what we did. But we apply graph convolutional embeddings in a way, or I should say, we construct graph convolutional embedding layer, right? We have already quite a few model-based context-aware recommendation methods. For example, probably most well-known are factorization machines, right? And factorization machines, what they do is they essentially compute embeddings for data that comes in the form of this array, right? Item, users, and context. So they compute embeddings for the representations of the items, the users, and the context in this array. But we can actually already compute representations from with graph convolutional network using this n-partite graph representation of the data. And then we can use factorization machines as a second layer, right, to the first graph convolutional layer that we have computed using graph convolutional networks, right? So basically we are taking this graph, we are computing the representations of the nodes and of the users in the context of and the items using graph convolutional networks. And these embeddings are then used inside the factorization machines. Of course, factorization machines compute and loss over these embeddings, et cetera, right? With a softmax layer or whatever other layer they have on top. And the gradients from that can be used in the graph convolutional layer, right? So essentially you have an end-to-end deep learning technique here, right? You have, let's say, the graph convolutional layer at the beginning, then you have the factorization machine layer at the as a second layer, then you have some kind of loss function over your recommendation, right? That can be a BPR loss or a categorical cross entropy loss or whatever other, and you can optimize that end to end using just backpropagation, right? And this is essentially trivial to construct with all the deep learning frameworks that they are, right? For example, TensorFlow and PyTorch, et cetera, right? And so, let me see, yeah, and we actually did this. We constructed this graph convolutional embeddings layer, and we tested it with four deep context-aware collaborative filtering methods. I mentioned for factorization machines. There was also neural factorization machines, deep factorization machines, and wide and deep, right? So we basically just use that as a basis. The first layer, right, is just GCE, graph convolutional embeddings, and then the rest is exactly factorization machines or neural factorization machines, et cetera, no? And not to bore you with too many results here, with the, oops, sorry. I'll just show you the results on one data set, which is actually a music data set, where we just used a very simple context. We just use the context of what the user listened to, what was exactly the previous song, right? So we have, and here you can see that just the results with simple factorization machines. And then the first is graph convolutional embeddings with factorization machines. And then we have graph convolutional embeddings, 2 layers of graph convolutional embeddings. We tried also 2 layers of graph convolutional embeddings at the beginning. And the same for neural factorization machines, deep factorization machines, and wide and deep methods. And you can see that basically there's quite a big jump in performance the moment you add this graph convolutional embeddings as an embedding layer into these techniques, right? Both at hit rate and NDCG. And it's actually not so surprising in some sense. Why is that? Because if you think about all these methods, and in particular, maybe the easiest way to think is about factorization machines, the explicit structure of the graph is never actually, of the graph that connects users, items, and context, is never actually used inside factorization machines, right? It's implicitly used, if you like, right? Because of the, in some sense, because of the loss function, right? But there's no, let's say, easy way to add into a model, context-aware model, the implicit structure or the explicit structure of the connections between the users, the items, and the context. Right? So here we actually doing this, and graph convolutional embedding is actually a very good way to do that, right? Because the model actually now becomes aware in some sense of the underlying graph structure, graph connections in the graph, right? And yeah, we will get quite significant improvements on all methods here, right? So this is essentially a way to add this type of information into the network. And let me quickly also talk about the second type of context I was mentioning, right? And this is the sort of typical session-based setting, right? Where you have a user entering a site, as I mentioned, and trying to purchase something, right? And here we know what the user's after, or we should understand what the user is after just by the actions of the user, by the first 2-3 actions of the user, right? And the data we are working with is essentially a sequence of actions of the user, typically a sequence of clicks, right? And we think that we should understand by these clicks what the context of the user is, right? What his aims are, right? What he's trying to buy, essentially, you know? And in this case, some computer hardware. Right? And you can think of most of the model-based approaches again here, work by modeling the sequence of actions with some generative sequential model, like, for example, like recurrent neural networks, convolutional neural networks, more recently transformer networks, et cetera, et cetera. What do? They basically take a sequence of interactions that the user's already done, right? And they try to predict the next interaction. No? And you can then think again of the internal state of that network, like, for example, in the case of a recurrent neural network, the internal hidden state of that network is a latent representation of the context of the user. No? So we have that network that is trained on all this data, and the internal state of the network while the user is clicking all this data and the network is taking in this data as an input is essentially a latent representation of the context of the user in some sense, no? of his aims of what he's trying to buy. No? And you know, you have all this, as I mentioned, this traditional sort of generative sequential models that are used. And the way these models are usually trained is by some self-supervised learning method. No? Think of, and by self-supervising, I mean, there's no external label to this data. We have only the sequence of events that the user has done, the sequence of clicks, for example. And what we always try is just to predict the next click. And the training procedure is actually exactly the same. We're just training the network to be very efficient in predicting the next click in the sequences of click, right? And this is the typical self-supervised learning that's also used in language models, and for example, like BERT and GPT. No? And so what is here the problem? The problem here, or let's say one of the problems here, is that in just trying to predict the next click and in just trying to reproduce exactly the data, right, we somehow, or maybe to some extent, maybe lose the aim or the actual objective of a recommendation. No? A loss function is a good tool for optimization. A loss function is a good tool to sort of learn patterns that are inside the data, but it might not be an optimal tool for actually making a recommendation as useful as possible to the user. No? We cannot really encode things like long-term recommendations for long-term user engagement. We cannot encode in a loss function in an efficient way diversity. We cannot encode their supply chain constraints. We cannot using click data potentially make good recommendations for purchases. Maybe our recommendations are going to be biased towards more clickbait rather than things that are useful to actually buy. You know, there are all these things that are difficult to include when you're just optimizing a loss function and an objective, right? In a strict objective and in a machine learning problem, if you like. Right? So, what's the solution? Well, people have been actually dealing with this problem quite a lot, and one of the solutions that seems to be quite interesting is reinforcement learning, right? In reinforcement learning, you actually can optimize almost an arbitrary reward, right? That you can define in some almost arbitrary way. You can say, okay, I want actually my user to actually buy things on my website. I don't want him just to be clicking around there, right? So then you can actually reward your machine learning objective or optimization problem whenever a user, or reward it more whenever a user actually buys something instead of just clicking on something, right? You can still reward clicks, but maybe buys more, right? So that would be sort of an intuitive thing to do. No, and there's a nice mapping between the reinforcement learning problem, where you have an agent that interacts with an environment by actions and understands receives from the environment the state of the environment and the reward, right? So there's a nice mapping between the classical reinforcement learning problem and the recommendation problem, namely the environment is essentially the user, right? The users. The actions are the items that we are recommending. The agent is our recommender system agent, right? The recommender system algorithm, if you like. And the state and the reward is obviously the recommendation objective, right? In this case, purchases or more diverse recommendations, right? And the state is basically all the previous actions that the user has done up to that point, right? We can from that define some kind of latent state of the user, right? There's some kind of latent context, if you like, right? So it's really a very good mapping, right, between reinforcement learning and the recommendation setting. But there are problems. First of all, we have a huge item space. There are all these items that we should recommend. I'm not going to go into the on-policy and off-policy problems, but in general, reinforcement learning requires an interaction with the user to learn, right? And if your model is not trained, this interaction will be very painful for the users, as the model will be doing completely random recommendations for a long time. And so ideally, you want to learn from log data. This is the off-policy learning problem, and that's really, really tricky in the recommendation setting. And people have been trying to build simulations for users and all that to recreate environments, but this is really tricky because model-based approaches, actually recreating the user's reactions is almost as difficult as creating a really efficient recommender system, right? So you're just shifting the problem away from the original problem. I'm going to skip the math notation here, and I'm just going to go maybe directly to the way we approach the problem. Well, basically, the way we approach the problem is by using Q-learning. And Q-learning is an off-policy reinforcement learning method, right? So in Q-learning, you essentially can learn from logged data. You can learn from your recommendation system logs, essentially. That's what it means. You can run this algorithm on your recommendation system data that you have collected, right? And the way Q-learning, the main sort of idea behind it is that we are trying to learn a function that, given the state that we are in, given the actions of the users up to now, given the state that we are in, and a given action, it should sort of predict what kind of reward we will get and what kind of potential future rewards, what we can get from that action, right? So you can think of it as an estimate of how much a given recommendation, given the previous actions of the user in that session, is useful towards our objective or not, right? This is really what the Q function is all about, right? It's really a match between where we are currently with the user and the recommendation we are thinking to do, and how much that is going to help us towards the goal or towards the objective that potentially is getting the user to find something useful to buy, right? And now that is a sort of typical, this is a classical sort of approach in reinforcement learning, right? There's gazillions of ways of solving that problem and learning the Q function. Really simple to implement, like 5 lines of Python code, essentially. But there is an issue here, right? There is an issue that is quite prevalent in recommendation system as well, right? Which is we don't have any negative feedback, right? We only essentially in recommendation, we always deal with positive feedback by the user, right? We know what the users clicked, what they potentially liked, but we never almost know what they didn't like, right? Especially if you don't have any rating data, no? And this is particularly problematic in this case because here we're doing a regression, right? So if we're constantly doing regression on positive data, on positive rewards, we're getting biased sort of Q values, right? Basically, our recommender system thinks, oh, everything's great, just recommend whatever because the user's going to click on something anyway, and it's going to buy something eventually anyway, right? So this is problematic, right? You don't get a nice learning out of that, right? And the way we deal with that is, let me skip directly to this figure. The way we deal with that is by basically taking a sequential model like the ones that are used in self-supervised learning, right? The classical sequential models that are used in session-based recommendation, like RNNs, as I mentioned, GRU for rec, etc., transformers, convolutional networks, and training it. We're training that with a classical approach, just trying to predict the next action of the user, the next click, which item is he going to click next, right? Same way. And we are adding to that a second output layer, right? And that second output layer is trained with Q-learning, right? So you can think of the Q-learning output layer as conditioning the sequential model to actually perform recommendations that are bringing us closer towards the reward that we want, right? And the reward in this case can be a purchase or more diverse recommendations or, let's say long-term engagement of the user or other things, right? And given that my time is running out, let me quickly go straight to the results here. And basically what this is telling you here is how much, what's the accuracy of that method to only purchases in the data sets. And we use the RecSys Challenge 15, the you choose data in this case, right? That includes purchases, by the way, clicks and purchases. See, when we reward purchase more than clicks, right, we get, these are two versions of the same method that we have implemented, right? Basically this slight sort of variation. But this is sort of a standard model that is trained only with normal loss function, trying to predict the next click. And these are the ones that are also with reinforcement learning. And you can see that the ones that are trained with reinforcement learning substantially increase the propensity of recommending items that are more likely to be purchased, right? In an offline evaluation setting, obviously, right? We haven't still yet tested it online, but that's pending. That's the aim of this quarter, actually. Right, and we used all sorts of different sequential recommendation models, GIU, Caser, NextedNet, and SASREC, right, which is the transformer-based model, and we get consistently the same results. So I think my time is finished. So yeah, thanks for listening, and if you have any questions, I'm not sure what's the format here, but let me know.
Thank you so much. We have 5 minutes. Actually 4 minutes for the questions. You can post them in whole in the chat. I will be happy to read them, or just simply unmute yourself and ask the question.
Hello, can you hear me?
Yes, Evgeny, we can hear you.
Hi. Alexander, thanks for the great talk. I wanted to ask about the format of the context. So you showed here that, okay, we have some contextual variables, then we also have some history about user behavior, the clicks and actions. Have you considered the option when the previous history is also treated as a context? So it can be treated as just interactions, but it can also be treated as a context. So at least like the short recent history can be viewed as a context. And I wonder, it's curious for me if you tried to model it like that. Mm-hmm.
Yes. Yes, we actually tried. If you've seen actually the previous method I mentioned, the graph convolutional embeddings, we used the context as context the previous interaction of the user. Exactly what you're saying, right? So we used this context the previous song that the user, and absolutely you can definitely do that, right? It's actually a very good idea in general to use the previous interactions, or previous 1, 2, 3 interactions as additional context to sort of if you like, boost the relevance of your recommendation, given sort of the previous actions of the users. Having said that, these methods here, right, these generative models, sequential models, they more or less do exactly that, right? So they take into account all the previous actions, and they build an internal state of all the previous actions, and they, given that internal state, recommend something new, right? So you have 2 approaches you can take here, right? You can either think of the previous items as really that's really the basis of your signal, right? You think of your recommendation problem as a sequence prediction problem, or you think of a recommendation problem as a link prediction problem, in which case the previous items form just a new type of node in your n-partite graph, right? So that's both very valid approaches to the problem.
Mm-hmm. Thanks. Yeah, I see.
Okay, thank you so much for your presentation. We are right on time, and we are switching for the next one. Please, Boning Gong, can you share the screen? Alex, can you please stop sharing the screen? So next presenter, share the screen. Boning.
Yes, I will try.
Yeah, please share the screen. So next we have a presentation of Boning Gong, who is going to present the work Contextual Personalized Re-Ranking of Music Recommendations Through Audio Features. Boning, you have 12 minutes for presentation and 3 minutes for questions and answers. Please.
All right, do you see my screen?
Yes. So make sure that you see me. I will show you the notification of time. Thank you.
Because I don't see you, but I'll keep track of 12 minutes. Hello, everyone. Welcome to my presentation on the contextual personalized re-ranking of music recommendations. I'm here on behalf of Mesut and David Interref. I'm presenting my master thesis work that I did at the Technical University of Delft as part of my thesis. So the agenda for the next 12 minutes, I'll first give a small introduction in the topic. I will give an overview of the research questions and the motivation behind the research. I will elaborate on the correlation analysis I did, the re-ranking experiment, after which I will conclude the work, give a short discussion on the work, and then we have a short Q&A session. So I want you guys to imagine two situations. On the left, you are lying on bed and you want to relax a bit and you're going to put in some music. On the right-hand side, you are in a gym and you're going to have a workout, and here you're going to put on music to get some energy. As you can imagine, in these two different situations, you might have different preferences for music. And in my research, I looked at how you can use this contextual information of a user to create more improved recommendations of songs that are more to a user's context. So the research questions that I try to answer here, there are 3 of them. The first is really looking at how are different contextual conditions related to audio features. So for example, which audio features do people prefer in the morning versus afternoon versus evening? Also,
Boning, so sorry for interrupting. We have some problems with hearing you. Maybe you can switch off your camera and so the connection will be better. The sound interrupts all the time.
There is a lot of echo.
Yep.
A lot of echo? Okay, let me
it's a little bit better, I think.
It's better now? More.
Yeah, it works. Please continue.
Okay, let me know if it's unclear. The research question looks at the re-ranking results. So basically, use this relation between the condition and what people prefer, which audio features people prefer. How can we rank recommendations, and will we get more accurate recommendations? And the third research question, we use 2 different models, a global model and a personalized model. And here we compare the results of these 2 models in terms of accuracy. So the research, the motivation behind the research, previous research has shown that context influence what kind of music people prefer, and also people like dislike songs based on audio features. So based on this, we look at audio features in different kinds of contextual conditions. Unlike a lot of previous research that we use in data spaces, we use a vector representation of audio features, which is more straightforward. And also, let's skip that part. So in the end, the goal of our research here is to have a straightforward and explainable contextual music recommender system that is using audio features. So for the first analysis, for the sake of time, I will not discuss what we've been doing, but to summarize, we looked at public playlists on Spotify, playlists that have been created for different contextual conditions. So people create playlists for in the morning or in the evening, but also for running, for studying, for focus, etc. And based on the audio features of the songs in these different playlists, we saw that there's a significant correlation between the audio features of these songs and the condition to which they relate. And then some are positive, some are negative, and it is also heavy audio feature and contextual condition specific. What we did see is that the audio feature of key was not significant, and the audio feature of liveness is it was weakly correlated. So based on the answer of this research question, we can use audio features to represent user preferences, to represent contextual conditions. So we created an experiment to re-rank recommendations, how this influences the results. For this, we used two datasets, of which the non-playing RS is the main dataset. It's the same dataset as Alex just referred to as well. We had to pre-process this dataset and extract the contextual data and the audio features of the songs that were in them for data usage. Then we proceeded to use this dataset as input for a regular recommender system. For this, we used the RecSys created by Bomshot and Young in Java. And this library, together with the input, would give us our initial recommendation list. This is just the list of songs that is recommended to a user, which will form an input together with the contextual data and the audio features for our re-ranking algorithm. And our re-ranking algorithm takes this list of initial recommendations and it will re-rank the songs. So the songs will be the same, but they will get a different order in the recommendation. And then here we'll evaluate the initial recommendation list with our re-ranked list based on its accuracy. And the goal is, of course, to increase accuracy based on the extra contextual data that we have now embedded in the recommender system. So for the dataset, a short description. It's created based on tweets. People were listening to a song, they tweeted about the song with an hashtag not playing. It's an implicit feedback, as we see often in this field, which means that we don't know, like we don't have negative feedback. We also don't know how much, to what extent people like the song that they listen to. So here we just assume that all interactions are positive interactions. We used a smaller subset because the dataset itself had millions of users, which is not usable for a recommender system to process all the songs. So we used a smaller subset here, and we focused on the contextual dimension of time of day, with the contextual conditions of morning, afternoon, evening, and night. Since this one was consistently available throughout the whole dataset. A bit more elaboration on our re-ranking model. So what we did here is we took audio features and we used audio features to represent what people prefer in different contextual conditions. So let me give a very concrete example. For example, we have this audio feature consisting of energy, acousticness, and some other audio features. Using this vector, we can represent, for example, morning and afternoon. In this example, people prefer low energy songs in the morning, but higher energy songs in the afternoon. And based on this representation, we came up with two different models. The first model is called the global model, and the second one, the personalized model. The difference here is that the global model, it uses all the ratings of all users to create the representation of what people prefer. So for example, if we take all attendees of this meeting right now, we might have a preference from like low energy songs in the morning and high acousticness songs in the morning. But in the personalized model, for each user, we calculate a specific vector representation for each condition. So in the personalized model, we can take 3 random people, and the first person, person A, might have a preference for high energy songs in the morning, whereas person B and C, they have a preference for lower energy songs. So this is how we model the preferences of users. And based on this preference, we calculate a new score for each song, and we give a new ranking based on the score. So also here another example, we have a preference vector for morning. We have different songs from Mozart and Chesto. As you can imagine, these two songs from totally different genres have different audio features. And here we use the formula, a similarity formula of 1 minus the normalized Euclidean distance between the audio feature vector of the song and the audio feature vector of the user preferences representation. And if you would apply this formula to this example, Mozart will have a score of 0.68 and the Chesto of 0.03, which means that the Mozart song is probably more suitable for a morning condition. And based on this new score, we came up with a formula that you can see below, the new score formula, where we use a lambda factor to give a weight to the similarity score and the initial recommendation score. So based on this, we carried out an experiment on the non-plain RS dataset with different parameters. So let me quickly elaborate one of these results. What you can see here is the experiment that has been carried out for 3 different initial algorithms. And the x-axis shows the lambda value. So lambda value of 1 means we only use the re-ranking similarity score. And a lambda value of 0 means we only use the initial recommender score. And on the y-axis, we have the mean average precision measured over the top 10 items. So basically, for each algorithm, we have 3 results. The baseline is the dashed result. The dotted result shows the re-ranking result for the global algorithm, and the solid line result shows the results for the personal model re-ranking. What we can see here is that the personal re-ranking, personal-based model re-ranking improves the accuracy for all 3 of them. Like it's a smaller improvement for the 2 above, but pretty significant improvement for the context-aware matrix factorization method. Also here, I want to refer to the paper if you want to see more results. So based on this, we can answer the questions. We saw that re-ranking is able to increase accuracy, but it is very case-specific. We need to configure all the parameters accordingly. Also, we saw that the personalized model consistently outperforms the global models, from which we can conclude that individual preferences models are more accurate, and different people have different preferences for different conditions. This is a bit computationally more expensive, but we think it is justified here. So in the end, we saw this correlation between what audio features users prefer and the complex condition they're in. Based on this relation, we created a vector of audio features to represent these user preferences. We re-ranked recommendations using these vectors by using a similarity score, and we saw that the results are promising. Also, we saw that personalized models consistently outperform the global models. Thus, we can conclude that we have a fairly straightforward and explainable contextual re-ranking algorithm to recommend songs to users in specific conditions. Short discussion, there are some limitations. So this research is, of course, limited to the domain of music recommendations, since we're using audio features. Also, we have been using audio features of Spotify. So if one tries to reproduce this study using different audio features, you might get different results. And also, there are some data-specific limitations. For the next steps, we plan to look at the importance of each audio feature. So in this research, we gave each audio feature that we have been using the same weight, but you can imagine that one audio feature might be more descriptive or more significant than another one. We also only did an offline evaluation using existing datasets, and online evaluation would be very valuable here. And next step is to combine multiple contextual dimensions. For example, on a user that's running in sunny weather, how you would combine the information on multiple contextual dimensions to create more accurate recommendations. So that's it. Thank you very much for your attention. And are there any questions?
Thank you so much for your presentation. We have a time for 1 question. So if you have questions, please post them to chat. I will be happy to read, or unmute yourself and ask your question.
Are there any questions? I don't think I can see the chat.
Okay, I don't see any questions in the chat. So let's thank the speaker again. Thank you so much for the presentation. Let's move to the next one.
Yes, thank you very much for having me. Yes.
Lee, can you start sharing your screen while I'm introducing you?
Okay. Can you hear me?
Yes, we can hear you. Give me a second to introduce you. It's my pleasure to introduce Dr. Lee Chen. She's currently working as an associate professor at Hong Kong Baptist University. Dr. Chen recent research focus had mainly been on recommender systems design and development, which integrates approaches of multiple disciplines, including artificial intelligence, human-computer interaction, user modeling, and user behavioral analytics. The application domain covers social media, e-commerce, and online education. Today, Dr. Li Chen will talk about user feedback on recommendations in conversational systems. So Dr. Li Chen, you have 30 minutes for presentation, 5 minutes for questions. Make sure that you see me. I will show you the science with time.
Okay, I can see you. Okay, thank you very much for the introduction, and thank you very much for inviting me to give this talk. So in this talk, I would like to introduce our group's recent work on understanding users' feedback in dialogue-based conversational recommender systems. So before I talk about our recent work, I would like to first give a very quick introduction of review of the traditional conversational recommender systems that have been mainly built on the graphical user interface. So actually over 20 years ago, so some researchers such as Robin Burke, so they have already started to think about how to better understand the user's preferences, especially in a product domain that the user is not very familiar with. So the users are very likely to be new users. So in that case, the user's initial preferences can be very uncertain, and they are not very clear about what they want. So they developed the Find Me, which actually is to allow users to see more examples and then allow users to give the feedback on the recommendation. And through this process, the user can be more familiar with the product domain and then can be more certain about what they need. So for example, in this interface, if the user is not very satisfied with this recommended apartment, the user can say, I would like to see something bigger or cheaper. And then in 2005, so Barry Smith's group, they developed this dynamic critiquing interface. And so in this interface, so the difference from Find Me is that they propose the compound critic. So compound critic operates over multiple attributes, such as less memory and lower resolution and cheaper. So if the user would like to see something that satisfies these three different dimensions, so the user can pick this critic. And also in the same year, so when I was a PhD student in Perth group, so we developed this critiquing interface. And so our focus actually has been mainly on stimulating users to make a trade-off among different attributes. Because according to the decision theory, the trade-off making is a kind of a compensatory decision strategy that can allow lead users to make a more rational and high quality decision. So that's why in this interface, we encourage users to think about which attributes are more important to you. And then in order to obtain the gains on these attributes, so maybe they're willing to compromise some attributes that are less important. So this can help the system to decide which solution, which item can be recommended to the user, especially if there's no available option that can satisfy all of the users, all of the preferences on the attributes. And also in the same year, so we can see the Francisco's group. So they also developed a critiquing interface on the mobile interface on the mobile device. So for example, the user can say they would like to see a restaurant with a nearer distance or farther distance. So the main component of these systems is the critiquing. And so the critiquing has been proven as a very effective feedback mechanism to allow users to construct their preferences. And also such kind of system has also been termed as conversational recommender system or conversational case-based reasoning system or knowledge-based systems. And so this is the basic workflow of the such system, and we call it actually is a critiquing-based recommender systems. So for example, so as you can see here, so we say the system first get the user's initial preferences. But this initial preferences doesn't lead to the final choice the user can make. Actually, it's the subsequent iterative critiquing process can assist the users in making more informed and more confident decisions. So the main focus actually is on involving users into a conversational interaction with the system to elicit the user's feedback. So as you can see here, after the system recommends some examples to the user, so the user can further revise their preferences while critiquing, and then the system can, based on the user's new preferences, to refine the model and then to update their the recommendations in the next cycle. And this can continue until the user finally makes the final choice. Oh, sorry. Okay, so actually our work has been motivated by the adaptive decision theory, and so we are mainly interested in studying in product domain that the user are not very familiar with, how to help them construct their preferences in a context-dependent and adaptive fashion. And so actually, this is to let the users be aware of their hidden preferences and latent preferences when they are able to see more examples, especially some examples, some products that cannot satisfy the user's preferences, and also maybe some preferences conflict that exist. And so by knowing these items, and so the user can have a more can be more certain about what they need, and also can make a trade-off among different attributes. So this can let the users make a rational and high quality decision. And so that's why we actually designed a series of critiquing interface. So starting with the user-initiated critiquing. So here the user can actually can be free to create the critiques on a single attribute or different on multiple attributes. And the user can also take any suggestion from the system if they are willing to compromise that attribute. And also we further developed the hybrid critiquing interface. So here we actually combine the user-initiated critiquing and the system-suggested critiques. And so as you can see here, so for among the system-suggested critique actually is to explain the trade-off relationship among different attributes, so as to let the users know that some, so for the recommended items, some can have a better values on some attributes, but they can have some negative aspects that the user need to be aware of. And also, we did a series of user studies and found that the critiquing system can significantly improve users' decision accuracy by 57%. And also the hybrid critiquing approach can give the users optimal user control, because the user can choose to either create the critiques by themselves, or they can pick the system suggested critic if it can exactly match what they want at that moment. And also recently, we tried to enrich the system suggested critic by incorporating the opinion features that we can extract from the product reviews to the customer reviews to the products, because we found that in previous work, they mainly focused on modeling users' preferences on static attributes such as price, weight, or size, but they didn't consider users' needs or their preferences on the opinion features that can be indicated by the other users, such as ease of use or image quality. So that's why we tried to provide such kind of sentiment-based critiquing method to the users, and we found that it can further improve users' product knowledge and their preference certainty. So now let's come to see the dialogue-based conversational recommender systems. So as we know that given the recent advance in the natural language understanding and generation, the dialogue-based systems, also called chatbot, has become very popular in many commercial applications. And also it has been found that in these systems, the user often seek for the recommendations from the system. For example, they may ask, can you recommend to me music to listen to, or can you recommend to me a movie to watch for tonight? And so compared to the traditional conversational recommender systems that have been built on the graphical user interface, so we see that the dialogue-based system can give the users more freedom, so the user can freely express their preferences in a way that they feel at ease. But we found that most of current dialogue-based conversational recommender system mainly focus on providing the one-shot recommendation. So that means actually they're more focused on how to generate the informative questions to ask the users. And then the dialogue will end when they returns one or a set of recommendations to the user. But in reality, the user can be unsatisfied with the current recommendation. So here's the challenging issues is that in such less controlled interaction setting, so how can we elicit the user's feedback on the recommendation if they're not satisfied with it? And how can we accurately understand their intents behind their utterance? And how can we further, predict their satisfaction with the recommendation? So this can, for example, if the user is not satisfied with the recommendation, so if the system can know it in advance, so the system can adjust its action and then can improve its recommendation to the user. And so, so that's why we have been engaged in addressing these issues, particularly in a multi-turn and mixed initiative dialogue-based system. So here, mixed initiative means that the user can initiate the conversation at any point of time. For example, ask the questions to the system, and the system can also initiate the conversation by asking some questions to the users. And so here, our focus is in our recent work. So we first did a user study, which was mainly to understand how user perceive the critiquing support if we incorporate it in the dialogue-based conversational recommender system, and also how about the user's interaction behavior in such system. And then furthermore, we want to construct a comprehensive taxonomy of users' intents for dialogue-based conversational recommendations. And also we want to predict the user's intents and their satisfaction with the recommendation in the dialogue-based CRS. So here is the workflow of the critiquing-based interaction in the dialogue system. You can see that it's actually quite similar to our previous conversational critiquing-based system built on graphical user interface. So we still first get the user's initial preference, and then the system recommends some candidates, and then the user can accept. And if the user do not accept, the user can make critiques. And as driven by our previous findings about the hybrid critiquing, we still support both user-initiated critiquing and also system-suggested critiquing. And another thing in this work is that we want to investigate the impacts of the user's personal characteristics on their perception of the system, also their behavior when they interact with the system, such as their desire for control, their domain knowledge. And so here, because we built a music chatbot, so we studied the impact of their musical sophistication and also their experience with chatbot and so on. And so here is the interface we designed for the music chatbot. So as you can see here, so we provide both the user-initiated critiquing. So for example, the user can say, oh, I don't like this song, I like a faster song. And the user can also critique on other attributes, other features. For example, they can say, I would like to listen to a song for dancing. And so this is user-initiated critiquing. And if the user doesn't know what critiques they want to post, but if they're still not very satisfied with the current recommendations, the user can click let bot suggest. And in this case, we will propose a critique to the user. For example, based on your current music preference, we think you might like the pop English songs with lower danceability. And so in our user study, so we compared the user initiated critiquing. So that means this dialogue system only with the user initiated critiquing versus with a hybrid critiquing. So that contains both user initiated critiquing and the system suggested critiques. And we ask the user to evaluate both interface, both systems within subjects set up. And so each user was assigned into 2 scenarios and to evaluate these 2 systems respectively. And so we measured both the user's perception of the system based on our the user-centric evaluation framework for recommended systems that Pearl and me have developed before. And we also included some questions about the user's perception, especially for the dialogue system, which was based on the Paradise, which is the evaluation framework for the spoken dialogue agents. And also we measured the user's objective behavior variables. And so here you can see the results. So this user study showed that there are not many significant differences between these 2 systems. But there's one significant difference that occurs on effort. And the user perceived that the hybrid critiquing in this system, they consumed more effort in looking for the sounds. But does it mean that so the user will also spend more time, or whether they also listened more sounds? Actually, through the analysis of their objective behavior, we found that they actually spent more time and also listened more sounds and also involved in more dialogue turns. And so that means from another point of view, so we think that this can imply that the user can be more engaged in using this system, can stay longer in interacting with the system. And we further analyzed the user's behavior in the hybrid critiquing dialogue system and found that almost half of the users actually, they didn't try the system suggested critique. So we further compared these 2 subgroups. One tried the SC system suggested critique, and the other subgroup, they tried the SC. And so we found that for the subgroups, they tried the system suggested critique, they found the system easier to use, and they also found that they listened to more diverse sounds. And so that means the SC can allow them to get more different and diverse recommendations. And also we found that some personal characteristics did take the influence on the user's perceptions. And so through the correlation analysis, we found that the music sophistication, if the user of high MS music sophistication, so the user feels that they have a high control of modifying their preferences when they use the system, and they are more likely to trust this system, and also they are more likely to give the feedback on the recommendation. And we also found for the people with a high desire for control, they also feel they have a high control of using the system. They also feel the system easy to understand, and also they know what they can do and what they can say at a certain point of time in the dialogue. And so in a short summary, so we say in this work, so we found that combining the user-initiated critiquing and the system-suggested critique in a dialogue-based conversational recommender system can help increase the user's engagement, and also can, especially the system-suggested critique can be likely to help the users to find more diverse sounds. And also we suggest that the interaction design of such system should better consider users' personal characteristics so that to make the interface can be more personalized and tailored to the user's personal needs. But there's some limitations of this work because as you can see that it is based on small scale user data. And also it is not very smart because it actually didn't consider other kinds of feedback that the user may have when they have the conversation with the system. So that's why in another work, we tried to establish a more comprehensive classification of users' intents when they interact with the dialogue-based conversational recommendations, and also to try to predict the user's intents and satisfaction with the recommendation. And so in terms of the user intent, the definition is that it indicates the user's goal or intention when they interact with the system. And the satisfaction refers to whether the user's goal is fulfilled to some extent. So in our case, in the recommender system, it means that whether the user can finally find some item they like. And so we say this is a typical architecture of a dialogue-based conversational system. So we say here, if we can know the user's intent, and also if we can predict the user's satisfaction, so the work's implication is that we can build a more accurate model of the user's preferences because we can better understand the user's needs, their requirements. And so this can allow the systems to know which actions they should take. For example, whether they should ask some questions to the user now, or whether they should, the system should recommend some items, or whether it should explain the item to the user. So in this work, we first analyzed a public data set as released in this paper, NIPS paper. And so in this paper, they collected a set of human-to-human dialogues. And so actually they recruited a number of Amazon mechanical turkers and asked them to pair with each other. So one worker acts as a seeker to seek for some movie recommendation, and another worker plays as a recommender to be responsible for giving the recommendation to the seeker. And so this is a real dialogue from this data set. So as you can see, during the interaction with the system, the seeker can have different kinds of feedback on the recommendation on the movie mentioned by the recommender. For example, this seeker said, I felt like it was too old for my tastes. I didn't like any of those movies, too much talking. I heard about that, but didn't watch it. We first cleaned this data set and then sampled two subsets. So one subset is, we call it is a satisfied dialogue data, because in each dialogue in this subset, the user, the seeker, liked at least one recommended movie. And another subset is, we call it is unsatisfactory dialogue data, because in this case, the seeker didn't accept any recommendation. And then by following the grounded theory approach, we manually labeled all of the utterances in this dialogue data. And then through several rounds of propose, refine, and annotate, we finally established a taxonomy of users' intents when they actually interact with the recommender. And so here we see there are three major top-level intents, which ask for recommendation, add details, and give feedback. And so we found that the give feedback, this intent occurs most frequently with 61.9%. And also here we see, in addition to accept, reject this feedback, The user can have other kinds of feedback, such as the seeker has seen the recommended item, or the seeker wants to know more about the recommended item, or the seeker wants to make the critique on specific features, or the seeker adds further constraints on top of the current recommendation, or seeker wants to say something similar to the current recommendation. So then based on this labeled annotated data set, we further tried to infer users' intents from their utterances. So here is the problem actually is given the user's current utterance, so whether we can infer the user's intent. So this actually is a label classification problem because in the user's input, it may contain more than one intent, such as in this example, there are 2 intents reject and the critic add. And so we actually tried different transformation strategies in order to transform the multi-label classification problem into single label classification problem, and then compared different machine learning standard machine learning models and also deep learning models. And so here actually it's very important to decide on which features we should input to the classifier. And so in addition to content, discourse, and sentiment categories of features, we particularly add a new type of features, which is context. So in this category of features, we considered the user's current utterance position in the current dialogue, and also this utterance similarity to the previous utterance, either from the user, from the seeker, or from the recommender, and also the previous tense, the user's intents, and the recommender's actions. And so as you can see here, so the comparison of the different machine learning models shows that the XGBoost performs better than the other models, no matter which transformation strategy was used. And another interesting finding is that we actually compared different combinations of the feature categories. And so, for example, in the case that only one category of features was considered, so the content category of features performs the best. But if we consider 2 categories of features, we find that the combination of content and the context features can achieve better performance. And also we found that the combination of all of these 4 categories of features can achieve the best performance among all of the comparisons. And also we tested, so with increasing of the number of dialogue turns that has been considered whether the performance will change. So here, 1 means that we only consider the previous interaction turns, user intents and the recommender actions, and 2 means that the previous 2 dialogue turns. And so as you can see that, so when the number of dialogue turns is 1, so this can achieve the best performance, and then the performance will decrease. So that means the latest conversation can be more relevant and useful to infer the intents, the user's intents. And then for the user satisfaction, we see this actually is a binary classification problem. And so we still compare different machine learning models, but here we didn't compare with the deep learning methods because these 2 methods we considered for the user intent prediction didn't perform well, maybe because of the small data set, relatively small data set in our case. And so here for the features used to predict the user's satisfaction, so we actually here's the problem is that given a number of dialogue turns, so whether we can predict the user satisfaction with the recommendation. So that is before the user accept or reject the recommendation we want to predict. So here we actually consider all of the utterances features. So in the previous number n dialogue turns, and also the dialogue behavior features. So that includes the previous N dialogue terms, user intent, and the recommender actions. And so here, so we found that the MLP, this machine learning method, performs better in terms of the precision and the F1 score. And then in terms of the feature categories, we found that the dialogue behavior features actually behaves the best, performs the best compared to the other categories of features. And another finding is that the combination of these 4 category of features actually didn't perform very well. So, and also here we also find that so once only if we just consider the previous turn only with 1 dialogue turn in the previous conversation, so this performs the best. But if we consider more dialogue turns, so this actually decreases the performance. So this further validates that so only the latest conversation can be more useful to predict the user satisfaction. And so in a short summary, so in this work, we established a taxonomy for users' intents and also tried to predict the users' intents and their satisfaction in the dialogue-based conversational system. So for the future work, we think there can be 2 directions. One is to further verify our taxonomy's generalizability to other domains, because in this work, we just used the movie recommendation dialogue data. And also we want to measure whether the deep learning methods can perform better if we can collect more dialogue data and label them. And also we want to investigate other potentially useful features such as the temporal sequence of utterances. And also in another direction, we want to further improve our interface design, and we want to integrate more feedback aids and to match to users' intents. And also we want to further improve the system suggested critiquing method in order to help the users, guide users to explore the product space to let them to get more diverse, interesting items. So thank you very much for your listening. And so I would like to thank my student, Ms. Wanling Cai, and also a collaborator, Yu Chenjing from the Lenovo Research Center, who have been involved into this work. Okay, and also I would like to say that we recently released our annotated data set of this recommendation dialogue data, and so which is public at this link, okay, for your interest. Okay, thank you very much for your listening.
Thank you, Dr. Li Chen, for the great presentation.
I overrun, right?
Do we have any questions? So again, please unmute yourself and ask your question, or type it in the chat. I would be happy to read. Any questions? No? Okay, so thank the speaker.
Okay, thank you.
Thank you so much. So
thank you for the invitation again. Thank you.
Thank you for being with us so late in your time.
Yeah, it's almost midnight. Okay, but it's okay. I'm still awake. Okay, thank you.
So right now we have a break for an hour. I will not stop this meeting. I will just switch off my camera. So please come back in an hour and we'll continue our sessions.
We think purchase intent and budget are 2 very important factors when for us to understand people behavior and people's intention when they using some e-commerce servers. So if we can predict the intent and the budget, so we may it may be useful for many things. For example, we can dynamically adjust recommendation and advertisement strategies, and even we can adjust our personalized promotions. It may also further improve our recommendation qualities. For example, if we can predict the budget of the final purchased item, then we may we can use this budget range to filter out some irrelevant items for recommendation. In terms of the recommendation strategies, one example would be if we detect a positive purchase intent for the user, then we may want to show alternative products for comparison, right? So the user can, through the comparison, he can choose one of them as the final purchase item. So we can show some alternative similar items. But instead, if we didn't detect a positive purchase intent, then the user may just want to browse, just may want to explore, right? So in this case, we can recommend diverse products to encourage exploration. So this is one use case of how can we use the prediction results of purchase intent. Okay, this is a real world user session. So this data, this session is not made up. So it's from real data. So Flipkart is the largest e-commerce website in India. And this is a real user session where there are 4 events. And you can see the user first browse the Redmi Note cell phone, and then he look at another another cell phone of from Oppo, and then it looks back to the Redmi phone, and finally it purchased the Redmi phone. So you can see on the right figure, these are the prediction results from our model. Okay, the red line is the purchased intent probability. So you can see as the time goes, our model can give prediction at each timestamp. That's why we call it dynamic. And you can see from the very beginning, the prediction probability is 0.5 and it goes up. So finally, the user purchased the item, right? And the blue one is the predicted budget. Okay. So in our case, we need to model different actions, content and context. For example, we have different action types. We have different content and even context, like time span, like device location. So how do we handle this? First, we embed all the above data, all the above feature into a D-dimensional space, and then we aggregate all the embedding at each timestamp. Okay, so each timestamp we have the item embedding and we have the position embedding. So this is for self-attention model where we have a position embedding for each timestamp. And then we have all the type, content, and context embeddings together. So we add them together. We also tried concatenation, but we didn't observe better performance. Okay, so the task would be at each timestamp t, given the embeddings of actions, we want to predict the budget and the purchase intent. So we tried a bunch of models, including the most simple one, bag of items, which we just simply add all the embeddings from previous actions. And we also try different neural sequential models, including RNN, TCN, and self-attention. Okay, due to the time limit, I will skip the, so this is just some figures to show how this kind of models works. So you can refer to corresponding papers for more details. However, our data sets are 2. The first one is mutuals, which is public, and the second one is internal, which is from Flipkart. And you can see there is interesting statistics here, which is in purchase session, there are many more repeat clicks. So user repeatedly clicks, the same item many times. While in non-purchase session, there are fewer repeated clicks. Okay, so this is the performance for intent prediction. So you can see with content and context feature and with even the count embedding. So count embedding means we used count information. The count information means how many times the user clicked this item before. Okay, we also embedded this feature. So you can see on the YouTube, so first trend would be if you have a content or context feature and even count feature, the performance will be better. Okay, another trend is self-attention is the best in YouTube, and RNN is best on the internal data sets. And also you can see the the sequential model like RNN, TCM, and the self-attention model are significantly better than bag of item baseline. So which, it's a non-sequential method. You just simply add all the previous items embedding. So you can see the advantage of sequential model here. The second task is budget prediction. And you can see the first trend is still, if we only use item, this group of method, we only use the item ID, and the second group use content and context feature. So you can see with more features, especially like the price information, we can significantly boost the performance. However, in this task, we didn't observe improvements for using the count embedding, right? The repeated clicks stuff. This might be because if a user repeatedly click the same item, so this might show he has a strong purchasing intent, but this may give us little information about his budget. So this is our one of the possible explanation. So we didn't add the count embedding here. And you can see the self-attention is the best over all the methods. Okay. And this is the performance in different session lengths. So for intent prediction, we did the improvements are like similar across all the session lengths. And for budget prediction, we can see for longer runs, the sequential model improves more. Okay, so finally the conclusion. So first we think, so we propose a new problem setting which predict the user intent and budget at each time step instead of like the beginning of the session or the end of the session. Okay, and we find sequential modeling is crucial for this dynamic program compared with non-sequential baselines like bag of items. And we also find the self-attention model is highly competitive for this task. We also find the modeling heterogeneous action types and the context information is very beneficial for understanding the both user intent and the budget. Finally, we found the content embeddings are useful for intent prediction, but not for budget prediction. Yeah, that's it. Any question?
Thank you, Wang, for your presentation. You can ask questions through the Wova chat or unmute your mic to ask questions.
This is David. I have a question here. Could you explain how to define the budget here? Is that the price you're going to purchase?
Yeah, good question. Okay, so the budget would be the final the price of the final purchased item. Okay, that would be the budget.
Okay, thank you.
Yeah.
Any other questions?
Yes, I have a question. I'm curious about how you define the context, so the variable of the context that you consider as important. Are these context variables that you just have, or did you do some evaluation and filtering and selection of the contextual variables?
Basically, these are all the context or content feature we have. So we use all of them, and we didn't do like a manual selection. And we feed all these features into the model, and we found a significant improvement.
Any other questions? One other question about the importance of context to the intent prediction. As I saw in one of your tables, you're trying to use the item ID plus the content and plus the content in the context. Have you tried to use only the content without any context and then see what is the importance on or the relevance of the context? How context really improve your prediction models?
Yeah. Although I didn't show the numbers here, but since in here, I think the content feature are very limited here, since as you can see this in the table here, right? So actually you can think like time span or context, right? Category is content. Price is actually it's context, since at different time the price may change. So we think it's context. And action type is also context. So you can see most of the side features are context. Only the category are content. So I did the experiment. So actually, at least in this setting, context feature helps more. Since, but it may also because we have more context feature. Yeah.
Mm-hmm. Great.
Maybe another question related to this one. So I saw in the results that with this internal data set, the improvement produced by the content and content is much higher than in the other data set. What is the explanation? So
you mean in this task or the second task?
Yeah, this one.
Yeah, this improves much. I think this is primarily because we have the price information. So you can imagine that if you only have item ID and you need to predict the budget, right? But you didn't know the price of the previous items, that might be hard. But if you have the content and the context feature, I think the price plays a very important role here. So you know the previous price, so it's very helpful for you to predict the budget.
Mm-hmm.
Thank you very much. Thank you very much, Wang Cheng, for your presentation.
Okay, thank you. Should I stop?
Yeah.
Okay.
Thank you.
Yeah, thank you.
And let's get the next presenter about towards quality of service aware recommendations by Savas Kastanakis. Savas, you can start.
Yes, can you hear me?
Yes.
So, and also, can you see my screen?
Yes.
Yeah, we can see your screen, but maybe you can, yeah, that's perfect. Thank you.
Nice. So, hello everyone. My name is Savas Kastanakis, and today I will present you our work called Towards QoS Aware Recommendations. So, as we know, recommendations are mainly based on user information. Let me put my pointer here, such as the user interests, the user history, channel subscriptions, and content and user similarity scores. Now, context-aware recommendations are based on both user and context information, such as the time of the day, the location, or the type of the device. They generate more relevant recommendations by adapting them to the specific context of the user. For example, a content might be relevant to a user at a given time of the day or at a given location, but not at another occasion. Now, similarly to other context parameters, the quality of service or the QoS with which a content is delivered to the end users may affect their experience, or the QoE, or even make them abandon the service. For example, a user may be interested in a video, but if there are a lot of rebufferings or low video quality, the user may lose the interest in watching that video. So, despite the intuition which suggests that QoS is important, QoS has not been considered as a dimension of the context yet. And we can say that recommendation systems nowadays are agnostic to the QoS. We propose to explicitly take QoS into account in recommendation systems for video and multimedia content delivery. So what we do is that we add the necessary network information in the pipeline of the recommendation system. Hence, the resulting recommendation list is a QoS-aware or network-aware recommendation list. This recommendation system scheme prioritizes high QoS videos over low QoS videos, or in other words, nudges recommendations towards high QoS content. This concept has been recently proposed, motivated, and studied from the network perspective, and initial results are very promising for the network capacity, the network congestion, or even the energy consumption. Also, it's reasonable to expect that user experience will be better. In fact, this is the assumption that previous works were based on, that users will be happy with QoS recommendations and that QoE will improve. And although this is a plausible assumption and expectation, however, it has not been tested with real users. And this is the goal of this work. Let's see through a simple example pretty quick, what QoS-aware recommendations are and some implications. Imagine that a Redois recommendation system would suggest the user video A. However, A QoS-aware recommendation system would recommend video B because a user would enjoy more high QoS video among two videos in which he is equally interested. For example, video A and video B. What would happen though if the ERS didn't have video B as an option? Would the ERS offer a less interesting video, for example, video C, with the intent to make up with better QoS? Our main goal is to provide experimental results and initial answers to some key questions that precede the adoption of a QoS-aware recommender system. For example, will users still click recommendations if these are modified to be QoS-aware? Do QoS-aware recommendations improve the user experience? And how much? And what is more important, the user interest in the video or the video quality? To answer these questions, we build an experimental platform that emulates a video service, emulates QoS impairments, and uses a simple QoS-aware recommender system. We conduct experiments with users, we collect the ratings and analyze the results. And finally, we propose statistical models to quantify the user QoE as a function of the video QoS and the user interest in it. We invited users to visit our platform and participate in our experiment through mailing lists and social media. The platform consists of three components: the video player, the recommendation list, and the rating section. Now, regarding the video player, we assumed that the network could deliver a set of videos in high QoS and all the remaining in lower QoS. For the low QoS videos, we emulated rebufferings since it's the most prominent QoS impairment in the literature. The recommendation list is a list of 5 recommendations given to the user when watching a video, and they are derived from a simple QoS-aware recommendation algorithm from the literature. The last component is the rating section, where we ask the user to rate his interest in the watching video, the quality of the video or QoS, the quality of recommendations or QOR, and the overall experience in the current experiment session or the QoE. Now, one important concern is that users might perceive the nudged recommendations as significantly worse and not be willing to select them because we sacrifice interest with the intent to make up with better quality. This could nullify the expected impact on both network performance and on user experience. For this reason, we first study whether users are willing to select these nudged recommendations. To quantify this, we plot on the x-axis the fraction of nudged recommendations for high QoS content, and on the y-axis, the frequency of selecting such content, or in other words, the click-through rate. Now, the blue line is the click-through rate for high QoS videos if the user selected randomly from the recommendation list. The red line is the observed click-through rate from literature and resembles the YouTube-like behavior, and the yellow dashed line is the observed click-through rate from the users in our experiment. In order to better understand how these metrics attempt to capture the impact of nudging, consider the following. Say that 2 out of 5 recommendations were nudged. If the user picked uniformly among the 5 original recommendations, then nudging could be considered non-intrusive if the click-through rate remains around 40%, while lower values would suggest that users tend to disregard the nudged recommendations. The click-through rate, though, is not just close to the uniform average, but well above. From this, we can state that nudging recommendations towards high QoS videos is not perceived as intrusive by the end users, and they are willing to click and follow these recommendations. And we are the first to provide experimental evidence for this. Now, let's get deeper into the factors that make users like QoS-aware recommendations. The table on the left shows the average user ratings for the QoS, the interest, the QOR, and the QoE among all high QoS and low video QoS and low QoS sessions. We see that the impact on users' interest and on users' perception of the recommendation quality, or the QOR, is more or less the same for both classes. On the other hand, the QoS of the videos is clearly perceived by the users, and this heavily affects the overall user experience. And from this, we can state that QoS-aware recommendations bring a positive impact on the overall user satisfaction. Now, the heat map on the right presents the average QoE for all different combinations of interest and QoS ratings, or in other words, the joint impact of interest and QoS on the user experience. What we can see from this heat map is that a video available in low QoS leads always to poor user experience, which is translated to less than 3 stars in average QoE, even when the users are very interested in the content, for example, 5 stars on interest. On the contrary, we observe that even when the users are not very interested in the video, their experience can be moderately good when the video is provided in high QoS. For example, the average QoE is higher than 3 stars for 2 in interest and 5 in QoS. So what we also derive from this table is that there is not a linear function to describe how QoS and interest affect QoE, or that nonlinear trends may exist in the relation between user interest, QoS, and QoE. The results presented so far indicate that QoS-aware recommendations can benefit the users, but is it worthwhile for content providers to adjust the recommendation systems to take QoS into account? Could this benefit their services, for example, improve the retention rates? We provide an initial answer to this in the figure on the right, where we present the average ratings for interest, QOR, and QoS, both for all video sessions, which are the dark colored bars, and for sessions after which the users abandon the experiment, which are the light colored bars. Now, these results can be interpreted as an analogy to the reasons that make users want to leave the video service. As we can see, the difference in average QOR ratings is negligible, while the ratings for interest and QoS are around 10 to 15% lower in the abandonment session. And this indicates that QoS is a factor of at least equal significance to user interest for the retention rates. So far, we presented the main findings from our experiments, that QoS-aware recommendations are not intrusive and that they can improve the user experience. Here, based on the collected data, we proceed to propose a model to capture the joint effect of interest and QoS on QoE, which, as shown before, may be complex and nonlinear. To achieve this goal, we use machine learning, and we select to model the interplay of QoS and interest with GLMs, generalized linear models, which allow us to capture complex effects, and at the same time, they're easily interpretable and can reveal insights. We carefully select the set of features to be used in such GLM, and then we design a model to predict QoE. Finally, we get that model, and we analyze its structure to derive interesting insights. The basic features that affect QoE, or the user experience, and for which we have explicit user ratings, are the interest, the QoS, and the QOR. To capture the more complex effects that the basic features have on QoE, we can use meta features, which are complex functions and combinations of the basic features. However, there are unlimited options for possible meta features, so we need to narrow down this set. And we use a feature importance approach to select only the most important features, but due to time restrictions, we omit the details of that process here, and you can find them in detail in the paper. The selected features are QoS, interest, and the minimum of QoS and interest. The question that is raised now is how important each of these features are, or in other words, how much do they affect QoE?
We are limited in time. Sorry for interrupting you. So just let's conclude it. Okay.
So pretty fast, I will say that the best performing model is ordinal regression. And if we study its structure, we can see that the most important feature is the minimum of QoS and interest. And this can be translated that recommender systems should get both QoS and user interest to satisfy a minimum standard. And then the recommender should pay more attention to the user interest. And I will conclude it pretty fast. In this work, we explicitly considered QoS as a parameter of the context, and we conducted real user experiments to provide evidence for the feasibility of QoS-aware recommender systems. Our findings suggest that users are willing to follow and click QoS-aware recommendations, and that QoS-aware recommendations bring a positive impact on user satisfaction and engagement. Also, that QoS should be taken into consideration when designing recommender systems. Although our work is preliminary, it is an important first step towards QoS-aware recommendations. And for that reason, your feedback would be extremely valuable. So please feel free to leave any comment or answer and make any question. Thank you for your time.
Thank you, Savas, for your presentation. We have time for one question. So either in the chat from the WOVA system or by unmuting your mic.
May I make the question?
Sure.
Can you, Okay, now it's an interesting topic, and it's an interesting presentation. But my impression is that this is more related to multi-criteria recommended systems rather than context-aware recommended systems. So we can consider the quality of service as a criteria for evaluating recommendations, and so the overall acceptance and the satisfaction for a recommendation can depend from multiple criteria. Can you also say describe your work in this sense?
So basically, I can understand your question, and indeed, QoS has not been considered a dimension of the context so far. So I can understand why you are classifying it in another topic, but that's the issue. We should take QoS into consideration. So when we speak about context. So imagine that you're watching a video with pretty low quality and you're totally interested in it. Isn't that a part of the environment that you're offered that recommendation?
Yeah,
I mean, the network condition.
You can consider this as environment, but it's like, let's say, in other recommended systems, I imagine hotel recommended system, the final, let's say, rating that you give to an hotel depends on the quality of service, the position of the hotel, I don't know, the cost, many criteria that summed up, they create a satisfaction. This is the same problem. So the appreciation that you have for a video depends on how you really enjoy the vision of the video, how you are interested. So these are multiple criteria that obviously are useful in order to predict the final satisfaction. But I would consider this more as a multi-criteria recommender system problem rather than context-aware problem.
Okay, great.
Okay, so thank you so much. Thank you again, Savas, for your presentation. And we'll proceed to the next presentation. Savas, can you stop sharing your screen so the next presenter can share your screen? So the next presentation is session-based KNNs with semantic suggestions for next item prediction by Miroslav Rak. Miroslav, you can share your screen.
Hello, can you please confirm if you hear me and see my screen?
Yes, we can
hear you and see your screen. Yeah. Can you see me during your presentation?
Sorry?
Can you see me during your presentation? I suppose you connected to Zoom through the HOVA.
Yes, I can.
Okay, so please track your time and be on time. You won't see my notifications.
Okay, thank you. So my name is Miroslav Rác. I will talk about the first results of my research related to my dissertation thesis. My co-authors Michal Kompan and Maria Bejlikova are also my supervisors. At first, let me give you some easy to comprehend notion of what we will talk about. Let's say you buy a coffee machine and you may know that it is not enough to have a machine. You need some other accessories for cleaning and maintenance. You need some coffee cups and much less coffee beans. And let's say that all these are concepts that complement or go with each other. But the question is, what is this relationship that relates these concepts together? We might find our answer in the idea of interactional view from Durisch, where the context is seen as a relational property between objects and activity. At the very beginning, the context triggers the activity, but as you may see in the picture, there is bidirectional influence between context and activity. So as activity proceeds, it inevitably changes the context in return. And since context influences the user preferences, they are not static. They evolve in the course of ongoing activity or a session. When you examine an average session from your data, you may see how the semantic meaning of actions changes all the time. Mostly the changes are so small that the semantics of consequent actions is practically the same. and you can label them with a single concept, for example, address. But occasionally there is a significant change, for example, from dress to shoes. So the takeaway from this slide is that we can devise a precondition that splits a session into several subsequences within which context is seemingly constant and among which drifts can be easily detected. The classical approach to the next item prediction is to calculate scores for all items and get the top n of them. But sometimes the highest ranked items do not match a user's context, that is to say, the user's current preferences, and therefore it might be a good idea to perform semantic post-filtering, which means to pick items that fit into current semantics, whatever their score is, and move them to the beginning of the recommendation list. We evaluated two types of such filters, which can differ in a way how the current semantic concept is derived. The first one exploits the length of coherent subsequences and the assumption that the item which is to be predicted will belong to the same concept as the action before. And the other type predicts the semantic concept, which is then used to post-filtering, for post-filtering. Especially in the first case, these conceptually coherent subsequences must be of a reasonable length, not too long, not too short. You will see why later. We can influence the average length by controlling the level of abstraction. For example, we can choose whether to use concepts high heels and ballerinas, or to use a single concept that involves them both and is called shoes. Actually, this is the subject of our experiments in which we measure the utility of different levels of abstraction. Either way, we have a two-level sequence modeling where the first level models dependencies on the level of items, and the second level models dependencies on the level of semantics. The result of the prediction of the second level are used to post-filter recommendations generated on the first level. Basically, concepts are clusters of items where clustering is made by the similarities of words from item titles. So at first, a word-to-vec model is trained on all item titles. In the second step, we calculate an average of word vectors from a title. In the first step, we perform spatial clustering using dbScan, where a range of different epsilon values is used. This is one of the aspects, one of the two aspects that have a significant influence on the abstraction. And the second aspect is linguistically based abstraction. That is to say, we do not use all words in the second step. We extract only most salient words which convey a high-level semantic meaning. Take this title as an example. Red striped dress with a silver zip on a back. So we parse the dependency tree that shows us the grammatical structure of the title. And we use 4 extraction rules, where the first rule takes only the root of the title and its first nominal modifier. And so the title is reduced towards dress and zip. Then each following rule gives a bit more details. The second rule expands to the second nominal modifier, so you can see that it's dress zip back. And then the third rules, this is the second, sorry. And then the third rule makes a bigger difference because it takes into account the root's adjectival modifiers. Therefore, it focuses on the visual appearances, such as colors and patterns, rather than on the functional features of an item. And the last, fourth rule makes no constraints and takes all the words into consideration. That is to say, all details, so it manifests the classical bag-of-force approach. To make recommendations, we use k-nearest neighbor approach with an extension providing sequential awareness. I believe that you are all well aware of similar KNN approaches, hence I will be very brief in this respect. So we have a scoring function that calculates a score of how much the tested item match the current sessions based on the item's co-occurrences or the item's dependencies. More information on this method can be found in the cited paper from Ludewig. What we have done, we added another weighting function that boosts items which match the current semantics. Since each item belongs to exactly one concept, the weighting function increases the score by 1 if there is a semantic match or by 0 otherwise. We use an evaluation scheme in which the task is to predict the immediate next item. Dataset contains 100,000 anonymous sessions from fashion e-commerce. Dataset is very sparse. The density is only 0.011%. As an evaluation metric, I will show you the results for MRR that calculates average position of the true item in a recommendation list. And since our task is to re-rank items, this metric is the most interesting. However, we provide a hit rate in the paper. So we make recommendations with 4 types of models. The baseline uses the scoring function without our extension, as I showed you a few slides before. The potential model uses a semantic weighting function that leaks the semantic information from the future. So it shows the maximum theoretical uplift that can be achieved with a particular semantic cluster set. And the last and predicted models, we already talked about them. So just to remind you how it works, in the first case, the following action is assumed to be of the same concept as the action before. And the second case, the model predicts both items and semantic concept. The concept prediction uses the same algorithm. The difference is only in the input. It takes a session represented as a sequence of concepts. So the top one prediction is used for the semantic post-filtering. Here you can see the uplift potential and the average cluster size with respect to the epsilon parameter for each configuration. You can notice similar trends for configurations which use adjectival modifiers, that is to say, a low-level information about appearances. And you can also see similar trends for configurations that omit this kind of information and use only the salient words. As one would expect, the smaller size of a cluster, the higher uplift potential. That is because smaller clusters are more constraining, but on the other hand, they are harder to predict. So we need to find a balance between the size and predictability.
Miroslav, we're out of time, so let's conclude.
Oh, it was quick, sorry. Okay, so the conclusion is that by the common sense, we understand that higher average coherence should provide higher benefit in MRR uplift, but this is not the case because you can see that there is larger coherence length, but the uplift is much lesser. And that is for a simple reason, that it is not merely the size of clusters that matters, but also their structure is very important because the conceptual coherence is inherently given by user behavior, and increasing it artificially for example, by employing larger clusters, is not inevitably beneficial. So, so the main contribution is the finding that the item generalization based on natural language analysis appears to provide a high potential for improving the recommendations. So thank you. I will happy to answer your questions, but it's been a long time since I spoke to people in English, so please speak on me slowly. Thank you.
Thank you very much, Miroslav. We have time for one question. Konstantin, do we have any questions from the WOVA platform?
Sorry?
No, we don't have questions on WOVA.
Great, so let's thank again Miroslav for your presentation. Thank you.
Thank you.
If you can, great, stop sharing your screen, great. And our next presenter, it is my pleasure to introduce Dr. Yong Zhang, which is currently an assistant professor at the Department of Information Technology and Management from Illinois Institute of Technology in Chicago. He obtained his PhD degree in Computer Information Sciences from DePaul University. As you all know, his topic of his PhD and also most of his research is in the area of context-aware recommender systems. And he published more than 40 publications in this area, including publishing the CARS kit, which is an open source library specifically designed for context-aware recommendation. Today, Dr. Zhongyang will talk about extending multiple contexts, extending context to multi-entity recommender systems. Young.
Okay, can you hear me?
Yeah.
Yes.
Okay.
Young, can you see me during your presentation? I will show you notifications. Okay, perfect.
Okay, no problem. Okay, so today I'm going to give the topic about extending context to multi-entity recommender systems. So there's two questions behind this topic. The first one, the question could be, can we build or use cars in the system that they don't have explicit context information? The second question could be, are there any connections between the cars and the other types of the recommender system for that? So my talk at the beginning, I will have a very quick revisit about the definition of the context, also the cars. So next I'm going to introduce our work. So how can we incorporate the context or conditions into other type of the recommender system for that? Okay, so first, let me introduce the context. Some general definition, simply context is any information that can be used to characterize the situation or the entity. So we believe that the entity here is the end user. So the situation here refers to the interactions between the user and the platform. So for example, the user may would like to listen to a song or playlist, or the user may would like to watch a movie or shop items. So all these behaviors can be considered as the interactions. So in this case, we believe the attribute of this interaction or this environment can be considered as the context. So for example, time, location, weather, budget, companion. So remember that those variables are not associated with the user only, or they are not associated with the item only. So they are the attribute from the interactions or environments. So in addition, we believe that there's some kind of the other variables from the user can also be considered as context. For example, user emotions, or the user objectives or intentions. Okay, the reason why, because every time when we try to perform these activities, so these variables may change. So give a more clear definition, simply, we believe that every time we try to repeat the same activity, for example, every time when I try to listen to the music, watch a movie, or shop the item, there's some variables, I mean, the value in the variables may change, and they may change frequently. So in this case, these variables can be considered as a context, right? Okay, so in the real world practice, the situation could be very complicated. So take the listening to the music, for one example, let's say at 3 p.m., so the user is going to listen to music. In this case, so she may care about the time and location. Then in the 5 p.m. again, listen to the music, but in this case, so she may care about the activities. So she'll be working out or driving in the car. And at night, again, listen to the music in this case. So occasion may be very important. So you can see that over the timeline, so different variables may be involved. Also, the importance of the variables may change. So that's the real practice. So the expert in this area actually put the context factors into different categories based on the 2 dimensions. The first one is whether the contextual factor may change or not. That could be static, that could be dynamic. So another one is whether we can observe the context. So are they fully observed, partially, or unobserved? Okay, so once we have the context information, so what is context awareness? So context awareness actually is not a new topic. So take this smart light for one example, right? So they do have the sensors. The sensor is able to identify my motions. After that, they are able to automatically turn on or turn off the lights. So in this case, this is one example of the context awareness. So any context-aware systems, they are adaptive ones. So they try to adapt the system output to the context information. So in the area of the recommender systems, so we assume that the user's taste may vary from context to context. In this case, we do hope that we can produce recommendations which can be adapted to the context situations. So that's the idea of the cars. Okay, so if we so the way to build a cars, actually, we do hope that the pattern may repeat. If the pattern is able to repeat, we are able to build a model to capture the pattern, right? So it depends on the pattern. I mean, they may change very frequently, or they may not change even the variables. In this case, there's research on the static cars, I think, which was popular in the previous 5 years. And I built the library cascade, which can be used in this case. Another type of the research could be interactive cars. So that's very popular in the recent years, including the session-based or conversational ones. Okay, so that's the quick review for that. So the next, I may have some kind of the question here. For example, let's say I want to build cars, but in my system, I do have a user item, I do have a user taste, but I didn't collect contact information before. So in this case, do I need to recollect contact information again? It's maybe very time consuming, maybe very cost expensive for that. Or can we extend the notion of the context so that we can still use context-aware models in my platform? So in this case, we do find out there's 2 terms. One is contextual, another one is conditional. So contextual prediction may produce predictions by giving a set of the context. But conditional predictions may make predictions by assume some conditions are true. Okay, for example, there's a term that's a conditional probability. You may not say contextual probability, right? So these 2 terms, I mean, they are very similar, but they may have some differences. So the question here could be, can we build conditional recommendations by using context-aware recommendation technology? Or simply, can we say, can we utilize conditions as context? So that's it's maybe a little bit confusing right now, but I'm going to give you more example for that. So next, I'm going to use a multi-entity recommender system as one example. So I gave the name multi-entity here, but it's maybe not that correct. A better name could be multi-dimension recommender system for that. So in this case, in the data, we have more dimensions rather than the user and items. So just for example, let's say context-aware recommender system, multi-criteria, and tag-based. They can all be considered as multi-dimensional ones. So let me give you a quick review for that. So context-aware, assume that the context variables are fully observed, then the data looks like this, right? So we have the user, item dimensions. So in addition, we also have context variables. Let's say time, location, and a companion. So that's the example of the context-aware. So multi-criteria, let's say take a TripAdvisor for one example, right? So when you try to give the rating to the hotel, so they are asking you to give the overall rating, but they are also asking you to give the multiple ratings on different criteria. Okay, if you got the data, it looks like this. So we have the user, we have item. In addition, we have the user rating in terms of the location, room size, cleanliness, or the item in this case, right? So that's the multi-criteria recommender system for that. So the last one is the tag-based recommender system. So in this case, we have the tag associated with the item. So user may assign the tag to the item, okay? But it's not necessary to have ratings. So in this data, we can see we have user, item, rating is optional, but we have multiple tags. So I'm showing 3 tag dimensions here, but you can imagine that could be thousands, millions of tags. Okay, so that's 3 types of the multi-entity or multi-dimension recommender system. So they have the same characteristics. So first, they have more than 2 dimensions. And these additional dimensions are not user demographic information, and they are not item features. So what are these dimensions? So they are either the attributes of the interactions, such as context, or they are the user interactions. For example, we have the user rating or the multiple criteria. Also, we have the tag usage, right? So in this case, these are the special characteristic of these additional dimensions. So the next, you can see that, particularly in the multi-criteria recommender system and in the tag-based recommender system, we don't have context variables at all. So the question here is, can we utilize the context-aware recommendation model in these platforms? Okay, so next I'm going to introduce how we can consider conditions as a context to be used. Okay, so we use a method called chains-based method. So this method actually came from classified chains. So it is used in the multi-label classification. So just for example, let's say we have multiple labels to make predictions. So in the first step, we are going to define a sequence of the labels. Okay, then we are going to use the original features to make a prediction on the first label. Once we have the prediction on the first label, this prediction will be added to the original features so that we can use this combination of the features to make a prediction for the next label. Once we have the prediction in the next label, the prediction will be added to the original feature. Then we repeat this process again until we finish all the processes in the predictions. So by using the classification chains, actually, first, we are able to capture the correlation among the labels. So the second, the idea is we consider that our prediction of the labels are true. We consider this condition as true, then try to make a prediction for the next. So this is one example how they use the conditions. So the second question could be, can we utilize the conditions as a context in these systems for that? So in this case, we build criteria chains, context chains, and tag chains. So next, let me introduce them one by one. Okay, the first one is called criteria chains, in which we apply the chains method to the areas of multi-criteria recommender system for that. Okay, so just give you one example. Let's say I'm going to book a hotel, let's say in Chicago, right? So in this case, I'm going to go to, let's say, booking.com. I'm going to use the Chicago as a query, then I get a list of the hotels, right? So in order to book the hotels, I'm going to read the user reviews. Okay, there could be multiple reviews. After the reading the reviews, I already have something in my mind. Let's see, the location may be very good, it's close to the train station. Okay, the room is very large, the hotel is very clean, and they do have very quick check-in, blah, blah, blah. So those tests actually, they are the multi-criteria test. So we already have the rating in mind. So the question could be, if we consider that we already have these tests in mind as conditions, so do we finally book these hotels? So that can be considered as a process of the multi-criteria decision-making process. So in this case, we built a technique called criteria chains. Okay, so just for example here, so we have the 3 rows. So we have user item rating. Also, we have the user rating in the room, check-in, and service. Okay, so to work on the criteria chains, so first we need to define a sequence. So that's a room check-in service. So what we are going to do? So I'm going to predict how user 3 will rate item T1 as the overall rating, right? So first I will predict how user 3 will rate the T1 in the criterion room. Okay, you can use any traditional recommendation algorithm to do that. So once you have the predicted rating, I will consider this predicted rating as additional input for the next step. So next step, I'm going to use the user item rating of the room and try to make a prediction how user 3 will rate the item on the criteria check-in. So similarly, the prediction of the check-in will be used in the next step so that I can utilize all this information, try to make prediction how user will rate on service. So finally, once I have these predicted multi-criteria ratings, we can use all of them to make a prediction on the overall rating. So that's you can see that in the step 2, we use the traditional recommendation predictions. But step 3, step 4, step 5, we use the previous prediction as input to the next step. So how can we use these previous predictions? We consider them as context. So the whole idea is assume that the user think that the room size is good. So how they will read check-in. Assume that they believe that the room is good, room size is good, check-in is quick, how they will read service. So that's the whole idea, okay? So step 3, step 4, step 5, you can use any context-aware recommendation model to make predictions. So that's the idea of the criteria chains. So the advantage in this method, so typically you can say we didn't develop the new algorithms, but instead we define a new pipeline, right? So in the pipeline, you can use any traditional algorithm to make predictions. And particularly, we try to use the previous prediction. We consider them as conditions or context and try to make prediction for the next. So the different challenges, first one, how to define the sequence in the chain. We try a different method, so information gain seems to be a good one. And also, it may be possible for us to define personalized chains for each individual user or for each user groups. But there's one drawback there is if you have wrong predictions in the previous step, then the prediction in the next may also be wrong. So that's the drawback for this technique. But this technique gives us a very good example. So the whole idea is we consider the previous prediction as context when we are able to make a prediction for the next. So in this case, even if there's no contextual variables in the data, but we can still use context-aware recommendation models. Okay, so the next one, the technique is called context chains. So even in the context-aware recommender system, we do have context variables, but we can still utilize this chain method in the cars. So how it works? So here I'm going to show 4 tables. So the first table, that's the original context-aware data. So we have the user, we have the item, also we have 3 context variables, time, location, and a companion. So what we are going to do? So first, similarly, we are going to define a sequence. Assume the sequence here is time, companion, and the location. Okay, so the first one, we are going to make a prediction by using the time dimension only. So in other words, we are going to make a prediction how user will read the item when time is weekend or weekday. We do that one by one. Okay. Once we have the predicted rating, we will attach the rating at the beginning, at the ending of the context condition. For example, in the table 2, you can say weekend 4. It means that the user may like the item in weekend. How they like them, rating 4. Okay, so that's the whole idea here. So once we have the prediction of the time, then we are going to work on the next one, companion. So in this case, we will consider the prediction at the time at the input, then try to make a prediction on the companion. So again, in this case, it means that but assume that you already like a weekend, that's a 4-star. So how will you rate the item if the context is the time plus companion? So in this case, we have predicted rating. We also put the predicted rating at the end of the context conditions. Finally, we will utilize the input time companion, then try to make a prediction on how user will rate items in the location. Okay. So finally, we have the data in the table 4. So the table 4 is the new data. So in the new data, we have predicted rating at the end of the context conditions. In this case, we create final grained context conditions, which can be used to finally make a prediction how user like the item in the original context. So step 1, step 2, step 3, so all those steps, you can use any traditional context-aware recommendation algorithms, right? So one drawback in this technique, so you can see we create final grained context conditions, but in this case, if there's a rating scale 1 to 5, so there may be multiple conditions created. So the sparsity will be increased significantly, right? So in this case, what we can do is we can convert this predicted rating into binary, 1, 0. So in this case, it's able to reduce the sparsity. Okay, how it works? So we compare the context chains with previous, popular context-aware recommendation models on this data set. So that's the result based on the MAE. You can see that they have almost over 6% improvement. And there's, in some data set, there's more than 10% for that. So there's 2 data sets, which is very important. First one is the food data set. In this case, actually, they have very dense context information. And if you look at the commodity data set, we have many context dimensions. We have many context conditions. You can see there's almost no improvement, only 0.3%. It's because that this method will increase sparsity, even if we use a binary predicted rating, right? But if your data is dense and you have limited number of the context, like the food data set, in this case, you can see it was improved, let's see, 15% for that. Okay, so the last one is tag chains. So in this case, we are going to apply this chain method in the tag-based recommendations. So tag chains, we are still working that in the progress, but the idea is very similar actually. If you look at the data, so you have user, item, also the tags associated with the item. But you may have millions, thousands of tags. So we cannot consider each tag as an individual dimension. So what we did is simply we cluster the tag into different groups. Each tag group is considered as a bag of the topics or the bag of the themes. Then we are going to use a similar method actually, try to work it on the tags. Okay, so I'm not going to give you more information about that. You can have brainstorming for that. Summary. Okay, let's go back to the previous question here. So that is, even if we don't have the context variables, so can we use conditions as a context to be used in this recommender system for that? So what we did simply, we try to incorporate conditional predictions in the chain. We make predictions by using the previous ones. The chain method simply defines a pipeline. You don't need to develop new algorithms. So you can use any previous algorithms to build the model. So in the chain-based method, we just add the user preferences to these additional dimensions, right? So in the cars, we add the user predicted rating in each context condition. So in the multi-criteria ones, we try to make a prediction on their criteria ratings. So in the tags, it's very similar. So in this case, we can still use the context rating prediction models, but there's no context variables at all in these models. Okay, so in this case, we give you one idea. Okay, that's probably, let's say, you can still use context-aware recommendation models, even if there's no context variables. Okay, that's all for my talk. Any questions?
Thank you very much, Young, for the great presentations. So Let's see if you have any other questions.
Hey, this is David. I have a question here. Actually, I try to confirm my understanding. Anyway, this is a great talk. It clarified a lot of my thoughts through your speech. So I think in the essence of your method, basically it tries to predict the context variable, and then you can utilize those context variables to get more accurate prediction for the rating. Is that correct?
Actually, here the idea is you can imagine that we consider the user taste as the context, then try to make a prediction about a user taste in another one. Okay, just take this criteria chain for one example, right? So we make a prediction how user like the item in terms of, let's say, the room size. Once we get the user taste on the room size, we consider that taste as a conditions or as a context. Then try to make a prediction how they like another aspect, let's say check-in, right?
Yeah.
All these tastes, we consider these predict taste as a context to make prediction for the next. Once we have all of them, we will utilize them as a context, then predict the overall rating.
Right, correct. So the basic requirement in order to this method to work is you still need to have enough data for the those tastes, right? In order to get the better prediction for some users who do not have their taste variable. Is that correct?
In my view, that is, as long as you can break down the decision process into different steps, then these steps can be considered as a sequence in a chain. Then you can use the previous step in the chain as a context, try to make a prediction of the next. So at the current stage, actually, we found that in this multi-dimensional data, so we can utilize them as the sequence in the chain. But in the other types of the data, you can imagine that as long as I mentioned, as long as you can break down the decision process into different sequence, I believe that you can still use this idea.
Okay, thank you.
Thank you. Any other questions?
Yes, I have a question. So just a curiosity about these criteria chains. So in some sense, is another way to solve this multi-criteria recommended system problems. Have you compared this approach with standard multi-criteria approaches where typically you predicted the single criteria and then you build a function that given the criteria, the individual criteria is then predicting the overall rating?
Okay, that's a very good question. So I didn't show the experimental result, but I can tell you that. So first we have the chain here because we want to incorporate correlations among these criteria. So the idea, you can imagine that if I don't like the room size, even if the check-in is good, I may not have a good impression on that. So that is your taste on one criterion may affect your taste on another one. So in our experiment, so that is we use a standard way. In this case, they are independent, right? So you can make prediction on user, how the user like the room, how user like check-in, how user like service. They are independent, right? So we compare this predictor rating with the predictor rating by using criteria chains. So we can demonstrate that we are able to improve individual predictions in each criteria. So that's the reason why the chains is able to take correlations into consideration.
Okay, thank you. That's interesting, but what is the order of dependency? Are you, let's say, finding out the right order, or is something that you try with all the possible orders?
Okay, so in our original paper, we tried 3 methods to define the sequence. The first one, we will make a prediction on each dimension, room, check-in, service. Then we will rank these dimensions by using prediction errors. So assumption is if the error is lower, then they should be put in the front. So this is one method. The second method is we consider the overall rating as a label and we consider room checking service as a feature. In this case, we consider it as a classification, right? So we use information gain, try to rank these 3 variables. This is the second method. So the last method, we use a random approach. Okay, we just randomly approach a sequence. Okay, so in our experiment, we found that by using information gain, it is much better.
Okay, seems reasonable. Thank you.
Thank you, Francesco. Another question that I had, Young, is kind of the same as Francesco, is how we can define the chains in multidimensional or in high dimensional contextual space. For example, in the IoT or in whereas like when we have contextual data gathered from mobile devices, for example, we have tons of contextual features. So how can we optimize those kind of sequences or change in the change in this kind of sense?
Okay, that's a good question. So if you have many dimensions, my suggestion first, you should reduce the number of dimensions first. Because if they have many dimensions and you work that in a chain, as I mentioned, if your previous predictions are wrong, then the next prediction may also be wrong. You can imagine if the chain is very long, then potentially you may have more errors, right? So in this case, we suggest you to select most useful dimensions first. Okay. After that, again, you can use the information again as the measure, try to rank these features.
Great, thank you. Any other questions? So if we don't have any other questions, before trying to conclude this presentation, which was great, I wanted to ask you, Young, about some future direction that do you see in the cars area research? What kind of potential future research direction do you see in that area?
Recently, I have one idea is that we can consider context-aware recommendation as a multi-objective process. The whole idea is that, say, you have multiple dimensions, multiple context variables, right? So you may like the item in some variables, but you may not like the items in some other variables. But finally, you need to make a decision that, say, given the context, that, say, given the 10 variables, whether you would like to pick up this item, right? But fundamentally, you may have the idea that, let's say, in the 5 variables, I do like the item in these 5 contexts, but in another 5 context, I don't like this item. But you cannot select the context because you are already within the environment, right? So in this case, the decision process can be considered as a multi-objective process. So that's my latest idea. Probably that could be a future research direction.
Great. And what about latent context? How can you see those, for example, the embeddings are incorporated in this kind of chains or the multi-criteria recommender systems?
Okay, so there's multiple deep learning model proposed right now. Most of them actually were used that's in the session-based recommender system. Also, there's some that was built for the traditional ones. But I mean, currently, as far as I know, the number of these papers, they are still very limited for that, right? So the first question I think is still it's very difficult to get context-aware data, right? So as far as I know, we still have these traditional data. They are very small, or they have very limited number of the context variables, or they are very sparse. So that's the first problem we have. The second one is, I mean, if you utilize deep learning models, it may not work well on small data. So we do need that a large data for the experiments, right? So that's the 2 barriers I can think about at the current stage.
And how do you see those chains used in the area of deep learning and so on? Do you think that it's reasonable to use those kind of chains in bigger data or in mass kind of data in context-aware recommendation?
If we do have large data, I do believe that deep learning could be useful. But the more interesting thing I want to work on is the explanations. How can we use context variables to explain how user make decisions? So are these context variables are the reasons user change decisions, or how the user adapt to this context to change their decisions? So the explanation, in my view, they are very important.
Yeah, I have a question regarding this. So you, Younger, did some research on quite a different problem, which not, let's say, making predictions about what are the items that are good in certain contexts, but what is the context which is good for certain items, no? So finding the best context. In some sense, what you are presenting here, also this criteria chains, maybe can be used in order to make, to elaborate, to find out in the data some dependencies between the contextual conditions. So maybe one can learn that when the room quality is very high, service is not any more important. And this would be very, very useful now in order to explain the meaning of context also in explanations. What do you think about this?
So I believe that the previous example is very important. Let me go to that. Okay, this one. So during the process of the user interactions, actually, the context variables involved may change. Also, the importance of the context may also change. If we are able to build some models, try to capture these changes, also we are able to understand that. So that's the big challenge, because as far as I know, even if we have the static model, but I believe that the context always changing. Also the pattern always changing. The only thing is we are assuming that the patterns are relatively static and they don't change very often. But in the real practice, you can imagine the user taste may even change over time, right? So in this case, if we are assuming that we have a set of the variables, okay, if we are able to detect that in which stage, which variable are important, and we can automatically turn up the weights in each stage, so that would be a great, contribution to this area.
Great, Young. So thank you so much for your presentation again. Thank you for joining us. And we are heading to the last closing remarks session. So I will give you, Alex, Professor Tuziling, the honor to lead the workshop closing remarks.
Hello again. First of all, I must apologize. We've been running 2 workshops in parallel, CARS workshop and Complex Recommended Systems workshop, both me and Bamshad Mubashir, so we keep switching between the 2. We have only a few minutes left, so perhaps it's a good idea to some reflections on what happened at this workshop. One thing which is really good to see how the idea of context and studies of context is still keeps broadening and extending to various situations and various new domains. Some of them were covered in this presentation. In particular, latent contextual information, a lot of work on this area, which is not surprising given the popularity of deep learning, where it fits very naturally. Also conversational recommended systems, where sort of context is studied. Multi-entity, as Young just presented. And another interesting connection is context and reinforcement learning, something which Alex addressed in his keynote. And sort of it's good to see how the concept of context is still broadening and expanding to new situations and also to new application domains. One thing which came during the break, which we discussed, it's still different authors put different meanings in what context is and what context is not. And unfortunately, within the remaining few minutes, we don't have time to discuss this big topic. Jung addressed it to some extent in his keynote, but still, perhaps maybe in the next workshop, we will revisit this question again. So we really need to put it down to rest, what context is, what context is not. So we're all of us on the same page. Because as I mentioned already during the break, we noticed, like, perhaps Moshe, you can give a couple of examples which you noticed.
Yeah, exactly. So as we saw in some of the presentation, each kind of author really took context to another kind of dimension. And of course, in each domain, there are certain type of contextual features which are very different. In one presentation, we've seen some explicit representation of context using the time of the day in the Spotify paper, whereas in the other ones, we talked about quality of service as the context, the conversational recommender systems, and of course, as Jung discussed, it can be multi-entity recommender system. Each entity could be used as a contextual dimension.
Mm-hmm. Yeah, perhaps we can in the workshop next year, we can revisit this topic again and allocate more time to these discussions. But also what I would like to address in the remaining 5 minutes is this question about the future research directions. It's like segue on what you, Moshe, asked Jung, and he answered from his perspective. Francesco also brought his perspective on this topic, but it's a sort of something which would be interesting to hear from the audience, any kind of feedback on what Jung said, on what Francesco said, or any thoughts which you have, where sort of the field is heading, what sort of interesting developments which lie ahead of us, what are the interesting research directions. So if you want to speak, there are not that many of us, right? Maybe you just simply unmute the microphone, or maybe type it on the chat on the online forum, so we can bring this. Anybody wants to address this question about future research directions of CARS?
Alex, if I can add something, I would mention something that comes to my mind, which I think is important. There is a huge discussion now on fairness of our recommended systems. I think when we introduce also the context, this concept of fairness in different contexts for different groups, it can become very, very complex. But it's very, very important because our recommended systems, the recommended systems that we're normally using, are customizing the recommendations based on the context, sometimes even more than based on the preference of the user. So this, I think, it's a topic that we haven't discussed. I haven't seen papers. Maybe I missed some of them, but I think it's another topic that could grow a lot and could be very, very important.
Alex, you are muted, so we cannot hear you.
Yeah, thanks. Yeah, I fully agree with you, Francesca. And this is perhaps the challenge to the participants of this workshop. So this is an important and interesting topic. And as a community, let's look into it. I fully agree, Francesca. Thanks. Any other comments, suggestions? And perhaps we only have a few minutes left. Anything which you want to discuss within the remaining few minutes? Related to future research direction or anything related to CARS. Questions? Are there some online comments? Can you check?
No comments, no.
No comments. Yeah. Well, I guess sort of this is like the remaining couple of minutes. But again, it's the question to the whole group. It doesn't have to be future research direction. Any suggestions for the workshop, what you liked, what you didn't like, anything which you want to discuss. This is your opportunity.
In my end, I think like the new research direction, as deep learning rising and reinforcement learning and so on in recommender systems, I think the explainability of latent contextual information would be very, very important to this area. So I think, and here I agree with Young, the explainability of cars is very important. And I think this is the next topic and very interesting one.
Okay. All right, to summarize, look, the nice thing about cars, we started it long time ago, the workshop on context-aware recommended systems, and then we stopped it for a few years because at that time we felt, look, we've done a lot of progress, sort of became mainstream, there's no need to do this workshop anymore. And last year we realized that there are all these interesting developments which are happening, which we just mentioned, and there are lots of interesting research directions. So we decided to resurrect this workshop. And I think Francesco would agree with me. Geddes is not here, right? And I know Moshe's and Konstantin's opinion. So I think we've done the right thing because there's still quite a few things to explore on this topic. Perhaps, be ready for the next CARS workshop next year, where we hope to see some papers addressing these new research directions, which Young, Francesca, and Moshe mentioned, and I also mentioned some of them. And also the field is growing, and the attendance this year was terrific. We had how many? 100-something participants. Moshe, what's the latest number? Constant.
On the peak, we had 130. In the first part, we had around 100 participants through the all the presentations, and in the second part, around 70, 80 participants.
Yeah, 130. I think it's a record. Francesco, correct me if I'm wrong, but I think the highest we had was probably 100 or so throughout these workshops. Great, so this brings the workshop to the conclusion. Thank you for the participants. Thank you for the keynote speakers. Young, thank you for your interesting presentation. And I hope to see you next year in the next CARS workshop. Thanks again.
Thank you, everyone.
Thank you.
Have a good day. Bye.
Thank you.
Bye-bye.